Have brief presentations from my panel. Then we'll open it up with questions starting here on the phone lines at centers, and also have our social media community have an opportunity to ask questions. Of course, you can get all of this information and the latest updates on Curiosity and all of NASA's Mars missions at www.nasa.gov/Mars. And join the conversation in the social media community. And there are a lot of people all around the world talking about Mars. Send your question into hashtag AskNASA and on Twitter @MarsCuriosity. Before we begin, coming to the podium to put things in context for everyone is the Associate Administrator for NASA's Science Mission Directorate. Please welcome Dr. John Grunsfeld.
Well, I'd like to welcome everyone to this press conference. This is just incredibly exciting for me. And I think once you hear the results, and I've not heard the detailed results yet, I think there'll be a tremendous amount of excitement. When we think about the Mars Science Laboratory event that we had last August, the landing of Curiosity on the planet Mars, often what comes to mind is the 7 minutes of terror. Well, since then we've had 7 months of anticipation for the results that you're going to hear about today. For me, one of the most remarkable things about the Curiosity rover is that everything is working. And I think that's just an incredible engineering feat. And I want to remind everyone who's listening that the amount of work that went into the results you'll hear is really been just incredibly intensive, has pushed human technology, has pushed what we're able to do not only on Earth with instrumentation, but on a planet that's tens of millions of miles away in a very difficult environment. I also want to remind everyone that what you're going to hear about are not the discoveries of Curiosity, but the discoveries of scientists here on Earth, and represented here today are those scientists. And it's not just the 4 folks who are up on the stage, but it represents hundreds of scientists working days and nights, and I think they've probably been doing ops, on nights and weekends, not because they have to, but because they love it, because this is what excites them, the fact that we're on Mars and that we have this analytical laboratory on Mars that's being controlled by the scientists and engineers and technicians from here on planet Earth. So with that, I will hand it over back to Dwayne, and I think this is going to be incredibly exciting. I know my anticipation is very high. Thank you.
Thank you, John, and that's a great segue, because now I get to introduce these incredible scientists, a small part of a tremendous team. First up, you'll hear from Michael Meyer, lead scientist, Mars Exploration Program, NASA Headquarters, Washington. John Gartzinger, Curiosity Project Scientist, California Institute of Technology, Pasadena, California. David Blake, Principal Investigator for Curiosity's Chemistry and Mineralogy Investigation at NASA's Ames Research Center, Moffattville, California. And Paul Mahaffey, Principal Investigator for Curiosity's Sample Analysis at Mars Investigation at NASA's Goddard Space Flight Center in Greenbelt, Maryland. So with that, turn it over to you, Michael.
Thanks, Dwayne. The NASA Mars Exploration Program has progressively approached the red planet from a global perspective to focus exploration of regions, past and present, that exhibit the potential for life. Every successive mission has boosted our expectations that Mars could have been a habitable planet, a place that could have supported life. This program of orbiters and landers have brought us to the point of seeking a habitable environment on Mars. This is what brought the rover Curiosity to Gale Crater. Mineralogical and geomorphological evidence from orbit showing that the area had significant amount of water in its past. As John mentioned, on August 6th, Curiosity landed spectacularly where we wanted in Gale Crater. Within 2 months, the team found an ancient riverbed, evidence of flowing water. And we followed that downhill to Yellowknife Bay. At the same time, we exercised the rover's capabilities, tested the instruments for the first time, and doing science along the way. We have now completed all the first-time activities, including the first sample drilled on another planet. This mission has been a fantastic team effort of engineers and scientists to deliver a highly capable exploration rover to Mars. The rover is now fully commissioned for science, all the instruments are working, and the keys to the rover have been turned over to the science team. Woohoo! So Mars has written its autobiography in the rocks of Gale Crater, and we just started deciphering that story. So chapter 1, Yellowknife Bay. This was an ancient environment with the right elements, minerals indicating a near neutral environment, and slightly salty liquid water. All the prerequisites to support life, a habitable environment. And so for the rest of the story, I'll turn this over to John.
Great, thanks, Michael. It's a great science story, as Michael was saying, and I need to start first with acknowledging our colleagues that came before us, and also the entire planetary community that supported this mission. As you know, developing MSL was a tremendous challenge, and we had plenty of adventures there, but we got the support from our community, and we really appreciate that. I'd also like to thank the Mars community, and through the leadership of Matt Gollenbeck and John Grant, which led to the final selection of landing sites that ultimately led us to Gale, where we have had a terrific time so far. That's been great. And also in particular, the MER mission, Spirit and Opportunity, Mars Express, and also Mars Reconnaissance Orbiter. If we have looked farther, it's because we have stood on the shoulders of giants, and those missions allowed us to fine-tune our exploration campaign that led us to this place. Finally, those of us that get to sit up here today are joined by our colleagues back at JPL and elsewhere, the other PIs of the mission, including Ken Edgett, Ralph Gellert, Don Hassler, Mike Malin, Igor Mitrofanov, and Roger Weens, and Javier Gomez Elvira. Every one of the instruments has led into the discovery that we have made here. Some of those instruments presented back in January when we first talked about the geology and that ChemCam discovered the first evidence for sulfates in this area here. You'll hear more results coming out next week at LPSC, and then at EGU over in Europe in April, you'll get to hear more still. So this has been a very comprehensive exercise, and we didn't just stumble into this area. This is something that took a lot of planning. Okay, so let me go to the first display item and bring you back to where we were the night of landing when we as a community first looked at this slide. We had selected a landing site, and the landing ellipse in particular was close to Mount Sharp, which was considered to be our primary objective. And so you can think about drilling an oil well here. You don't just go in with one objective, you need primary objectives and you want secondary objectives. And we had a secondary objective, which was the distal part of this alluvial fan that you see here in the landing ellipse. And we needed this in the back pocket in order to have the landing site confirmed by the review board and then eventually accepted by headquarters. And in case something happened to the rover, we needed to make sure we had science to do in that landing ellipse. But that was sort of you can think of it as a backup or a secondary objective, and it turns out now, in fact, to have become our primary objective at this point. We landed at there where it says Curiosity Landing Site, and we drove just a few hundred meters in the opposite direction. We did this deliberately, and this was based on the mapping that the science team did in advance of landing, and based on the previous mapping that came from Odyssey and MRO and all those great missions before us. And in this particular case, it led to the deliberate discovery. So it wasn't serendipity or luck that got us here. It was the result of planning. Now, what Paul and Dave will tell you about is the part that we do consider serendipitous. We had no idea that we were going to go into the aqueous environment that we were predicting to exist here, and also find sulfates and also find clays, and those guys will tell you about it. So that's one of the reasons that we're going to be spending some time here. So let me turn it over to Dave, and he can tell you about Kemen.
Well, thanks, John. And we got really excited when we first saw these bedrock at John Klein and saw these concretions. And the reason is concretions are evidence of a water-soaked sediment, a soft sediment. But what kind of an environment was it? Was it ever habitable for life? And if it was, would it preserve the organics for literally billions of years until we came here to take a look to see if we could see what was there? If you turn to the first graphic, you can see what made us think we really found something special. Okay, well, this is what we call pay dirt. This powder in the scoop here is from John Klein, the drill powder, and it's gray-green, meaning that it wasn't highly oxidized. And you can see in the back of the scoop there's a little bit of reddish material. This is from the rock nest, and this is highly oxidized. So anyway, what it shows you is that this material was never highly oxidized, and therefore, if there was organic material present there, it could have been preserved. The second graphic shows a comparison of the two X-ray diffraction patterns that Kemen has collected so far. On the left is rock nest soil, and on the right is the pattern we got recently from John Klein. You can see they look very similar, and from our analyses, we can tell you they both have igneous minerals, feldspar, pyroxene, olivine, and magnetite. What's different, if you look at the John Klein diffraction pattern, down close to the central point there, the intensity is due to clay minerals, and you see they're labeled phyllosilicates. And we can tell you from our analysis there's between 20 and 30% of a phyllosilicate called smectite, and that smectite forms in the presence of water. We know that. In addition, we have evidence of salts like halite and calcium sulfates rather than iron or magnesium sulfates that were found at Meridiani. And this suggests that the water was relatively neutral pH, and in other words, it was a potential habitable environment. So all of this is what mineralogy can tell you from an ancient surface that's billions of years old. So the next graphic shows you what we think a good terrestrial analog is for this material we found in Yellowknife Bay. The left image shows a clay-bearing sediment deposited in a lake bed in southern Australia. And on the right, you see a core of this sediment, and the different layers in the core represent different changes in mineral composition as the lake sediment was deposited. With that, I'll let Paul talk about what the SAM instrument found.
Thanks, Dave. Just delighted to show you some results from SAM. And I'm going to explain a little bit about how we did this fairly complex experiment. But I thought it would be fun to bring along what's a full-size scale model of SAM, the Sample Analysis at Mars experiment. SAM and Kemen are both buried deep inside of Curiosity, so in these kind of beautiful self-portraits that Ken Edgett's camera takes of Curiosity. You don't see much of SAM and Kemen. We have a test bed up at Goddard. You don't see much of it either because it's an environmental chamber. It's buried deep inside an environment that represents Mars. So here we've kind of taken away the aluminum paneling and put on plexiglass and made a model. And where the experiment starts that I'm going to describe, we have just a little bit of sample located inside a SAM cup. And I went last night into Amy McAdams' lab up at Goddard and dug around and found some nontronite, which is a clay mineral of the type that we're going to be talking about today. And there was a scale in there, and I weighed out 45 thousandths of a gram of that stuff, because that's about the amount that was in our SAM cup when we analyzed it. So that's where the story of this analysis that I'm going to tell you starts. We have the sample in the cup in SAM. We have loaded it the previous sol, the previous day, and we're ready to do our analysis. So it's night on Mars. The rover's gone to sleep. SAM's kind of a night owl. We like to operate at night, and nobody else there to bother us. But it's also a good thermal environment for some of the instruments to operate. And so we had put the sample in the cup through this little inlet tube. This vibrates as the sample's going into the cup. And then the sample manipulation system developed by our collaborators at Honeybee Robotics can be seen down here. And it Turns out that the way the sample gets to the oven is this little carousel rotates.